Today we're going to be reviewing interest, which is something you should have seen before, and we're going to sort of expand into one new interest formula this year. So when we're talking about interest, we might see something like this. $10,000 is invested in an annual interest rate of 10%. If you're ever watching TV or you see a commercial, you might see something like APR. That's what that is, annual percentage rate. So we want to find an equation that represents the amount of money after t years. This is what we call simple interest, and it's simple because it's just per year. Right? There's nothing that tells us anything weird, so this interest rate is just per year. That's what simple means. And so our formula for this is going to look like this. A of t equals p 1 plus r to the t. And so here, t is the time in years. R is our rate. The thing we need to be very careful about here is this rate needs to be a decimal less than 1. So 10% is R equals 0.1. We move our decimal place forward 2 to convert it into the decimal or the proportion form. Then we have this P. P is principal or starting amount. And then A of t is amount after time t. So this is what our simple interest rate formula looks like. This is not how most things, like with money that we work with, like banks, loans, mortgages, credit cards, that's not per year. If you think about it, there are monthly statements for stuff like this. So they get compounded. What that means is that our rate is distributed throughout the year. And what it really means in sort of context is that there is interest on interest. So if, for example, we owed $500 and then month 2 we had $5 of interest, then the next time it's not $5 of interest, it's maybe $5.50. Oops. So the amount of interest each month goes up because we're gaining interest on this interest. So it's not $500 anymore. We're getting interest on $505 if we don't pay this stuff off. So it's sort of, it compounds or it sort of grows on itself. That can be very bad if we're not careful, especially with money. So let's think about our interest again. And so in this formula, this is what our formula looks like. And here, if we had 10%, that's going to look like A of t equals our principal here is this $10,000. And then we have 1 plus 0.1, because we got to use our decimal, to the t. And so we can change this 1 plus 0.1 to 1.1. This is 1.1 because we have to take everything we already had, that's the 1, and an additional 10%. That's why we get that number, and that's why we have that 1 here. It's our principal and the rate. Okay. So what if we compound at different time intervals, right? And our rate is split. What is that going to look like? What's our rate actually going to be at our different time intervals? Well, so if we have 10% yearly, each time we compound, it's 10% or 0.1. Right? So these are our R's. If it's quarterly, quarterly is 4 times. So it's going to be R divided by 4 each time because we distribute our rate across the year. So we distribute that 10% to the 4 times at 0.025. So that's our interest rate at each instance. If it's monthly, that's 12 times. So we're going to divide our rate over the 12 monthly compoundings. Oops, put this down here. And so we're going to get 0.1 divided by 12, 0.0083 repeating. If it's daily, that's 365. And so we're going to have 0.1 divided by 365. And we get 0.000274. Now on your calculator, this might look like 2.74 e negative 4. What this e negative 4 means is that we have to move the decimal place this way 4 times. 1, 2, 3, 4, 0, 0, 0. So we need to know this is scientific notation. And so if we compound n number of times, this would be 0.1 divided by n, and in general it's just r divided by n. And n times means we have n times per year, obviously. Yearly would mean 1. So let's think about how we can go from simple interest to compounding interest. So our simple interest formula looks like this. P times 1 plus r to the t. This is a of t. Remember, a of t is amount after t, and then most of the time we talk about years, but we could measure this in hours, sort of depends. P is our principal or our starting amount. R is our rate, but it's got to be a proportion. That is so important. N is the number of times compounded per year, or per whatever t, like, so per year, per month, it depends on what your unit of t is. So we'll say per t unit. Most of the time that's year. And t is our time, and it has some units. Often this is years. Doesn't have to be though. So let's think about this. Our amount after time t is not going to change when we go to compounding interest. We're still looking for amount after some amount of time. Our principal also doesn't change whether it's compounding or simple interest. We still have a starting amount. We're always going to have that 1 because we're going to take whatever this is plus the interest. Our rate now, we said we distribute, that becomes r over n. And so then this is the question. What goes up here? And so you might think it's t, but it's not, because up here should be the number of total interest as it counts. The total number of times we calculate interest. And so if we're compounding 4 times a year, then there's 4 for 1 year, right? If we do 2 years, that'd be 8 times. And so in general, we're going to have 4 times the number of years. That's the number of times we take interest. Similar, monthly, for 1 year, we do that 12 times. For 2 years, do it 24 times, etc. And so if it's n times t is the number of times we have to calculate our interest. And so up here is going to go nt. These are the things we're most likely to forget, especially this one up here, that n times t. That's super important. So this is our simple and our compounding interest. Notice if n is equal to 1, which is what it would be for yearly, right? Just 1 time per every year. If n is 1, that would mean we compound yearly, which is not really any compounding if we think about it, but we get a of t equals p times 1 plus r over 1 times 1t, and that's exactly this formula. So really, this describes both cases. It's just that simple interest can be a fairly common thing. So it's not bad to remember this formula. The only other thing I'm going to say about this is that if we are going down, so decreasing values or amounts, have negative rates. And so that means in our formula, we're going to have a minus here because this R will be a negative. So just keep that in mind. It is possible to get a negative sign. We call that, if you remember, decay. Whereas if they're positive, then they're growing. And we'll read that more when we talk about our exponential graphs. So now let's sort of expand out into some new stuff. So if we think about nature and how the world works, if you take medicine, how does that work? You take your medicine, it sort of activates, and then over time it goes away, which is why then maybe you have to take more medicine, right? If you take like Dayquil, it's going to wear off eventually. So once it activates, does it decay in your body every hour on the hour? So like we have this we have maybe 5 milligrams in our body, and then the next hour it jumps down to 2.5 maybe, and then it jumps down to 1.25, and etc. Does it jump down like that? So no, not really, right? It decays what we would call continuously. Think about it like this. If we start with 5 milligrams, then it's just always going to be going down. Maybe it doesn't go down exactly like this. Maybe it goes down like slowly, or maybe it goes down really quickly, right? So there's some different options here for how it might sort of go down, but it's going to go down at like all the time. Every second, every millisecond, that medicine is working and it's using up, right? It's going away. So it's not this like stair-stepping, which is really what we're doing up here, is we're saying every month it goes down, or every day it goes down, or every hour, right? This is literally at every second it is changing. At every millisecond it's changing. So what does that mean at n? That means it compounds an infinite number of times, right? So n equals infinity. Well, that's not really a thing we say, right? We say that n goes to infinity. And so we get some interesting behavior here that we're going to look at in a later activity. But what happens is we get this, what we call natural number that it goes to, called e. So e is a number. If we look in Desmos, and I type in e, it actually gives me a number. This is like pi. It doesn't end. 2.71828182846, etc. It does not end. It's a non-repeating decimal. Like pi. Very similar to pi. And so we end up getting, and we'll look at sort of how we get this later. We get a of t equals p e to the rt. And so a, p, r, and t are exactly the same. E is just a number, and it's called Euler's number. Euler is a famous mathematician. And so there are lots of natural processes that work this way. One classic example is radioactive decay, or half-life, which is how we carbon date objects to find out how old they are. We do need some additional tools to sort of work with that problem. And so we'll come back to half-life problems a little bit later once we look at logs. So let's do some practice problems to review these formulas. So in our first example, we have Luke bought a new car for $34,000. The value of the car depreciated by 13% each year. Find the value of Luke's car after 3 years. All right, so the first thing we have is depreciated. Depreciated means down. This is decay, which means that our R value is going to be negative. And we've got to convert that percentage into a proportion. So we have r equals negative 0.13. And we want to find the value after 3 years. So that means t is going to be 3, and we're looking for what is a of 3. This 34,000 is our principal, p. So if we set up our equation, it's going to be, remember this is our equation, a of t equals p times 1 plus, we need to think, is this compounding? No, it doesn't say anything about compounding or number of times per year. So we're going to stick with this, r to the t. And so if we put everything in, we've got a of 3 is what we're looking for, equals our principal, 34,000, times 1, r is negative 0.13, to the t, which is 3. And so we just put this into our calculator. We're looking for 34,000 times 1 minus 0.13 to the third. And so we get 22,389 point, and we're going to say 10. This is money, and money has 2 decimal places, so that's how we decide where we're going to round. Think about the context. What seems reasonable? For money, it should be 2 decimal places. Let's do our next one. Addie inherited a diamond ring that was purchased 20 years ago for $500. So $500 is our principal. The value of the ring increased, so that means the rate is positive, by 8% per year. What's the value of Addie's ring today? So we're looking for what is the value. So it's a of t is what we want. Right? We know that our r is going to be 0.08 because we've got to move our decimal place twice. That puts a 0 in front. Our principal is 500, and t, that's 20 years ago from today. So we want our a of t equals, we're going to use simple interest again because it doesn't say anything about compounding. We're going to have 500 times 1 plus, because our rate is positive, we know 8, to the 20. We could combine 1 plus 0.08 to be 1.08. That would be fine. All right. So we got 500 times 1 plus 0.8 would be 1.08 to the 20. And we get 2,330 point, let's round up, $48. Remember this is dollars, so we're going to give it 2 decimal places. So that would be our answer. Okay. So let's say Juan purchased a television for $800 using a credit card. The interest is charged on any unpaid balance at an annual rate of 23%. That, well, it might seem high, is actually maybe not that much. I would say annual percentage rates on credit cards can be anywhere from like maybe 12% to, they can get pretty high, like in the 40s. Depends on your credit. So the better your credit is, the lower your annual rate might be. It also depends. Some credit cards are just a flat, everybody gets the same rate. So that's why a lot of times people like shop around for credit cards. Like some credit cards are better than others. A lot of credit cards also have a 0% rate for like the first year if you qualify, meaning you have good credit. And you have good credit if you have a history of making timely payments and you have a history of having credit accounts like bank loans, school loans, mortgages, other credit cards. And so this is how people determine whether to risk giving you money and giving you credit or not. All right, so this says compounded monthly. So this tells us that we're compounding, and the monthly part tells us that n equals 12 times a year. So we're going to say Juan makes no payments for 1 year. So we're not taking anything away. This is just going up. That G got weird. Going up. How much will he end at the end of the year? So our T here is going to be 1. And so this is compounding interest, so we're going to use this formula. A of T equals P times 1 plus R over N to the N T. And so our R is going to be 0.23 because we've got to make it a decimal or a proportion. And interest is something we accrue or something that goes up. So that means R is positive. This interest is always more money we owe, right? And so this 800 is our principal amount. So when we put all that into our formula, we get A of T equals 800 times 1 plus 0.23 divided by 12 to the 12 times 1. So we're just putting in all of those values we found. A of T is our amount or how much we're going to owe at the end of the year. So we want to find that value. So we're going to plug all this in. We've got 800 times 1 plus 0.23 divided by 12 to the 12th. Now notice every time I do this, I'm putting the whole thing into my calculator. It's in your best interest to do that because these numbers, we've got the 1 plus our rate to the power, can sometimes get small or get big, and our calculator does a better job of calculating things, and we're more likely to avoid things like rounding error if we just put it all in one go. So we want to try and put in as much into our calculator as we can at once so we don't have any sort of compounding errors where we get errors on errors on errors and they just get bigger and bigger and it gets bad. So what we get is that he would owe $1,000, $1,004.69. That's that's almost $205 more. And so this is a problem with credit cards, is that if we don't pay them off, you can end up paying significantly more than you ever thought you would if we avoid payments. Now, with credit cards, if he put this on his credit card and then went home and paid it off, there's no interest. But you might get like points or bonuses or even cash back from your credit card, and so it can only almost be like a discount. So depending on how you use a credit card, it could be a good thing or it could be a very bad thing. If you're not good at paying off your credit card, or you don't have the money to pay off your credit card, then this interest can grow out of hand, and the next thing you know, you have $15,000 of debt that you're paying off every month. And so that's how credit cards get people in trouble. So the moral of this story is, if you can pay it off when you go home, put it on your credit card, pay it off when you get home, and get some bonus points. If you can't, then you need to really consider whether you need that or not, right? That's my life advice for you. All right. Let's look at some more. Ellie deposited $2,000 in an account. Okay, that's our principal. She deposited that. That's our starting amount, P. It pays 4.5 interest compounded continuously. Oh, we have an interesting word here, continuously. We've seen that before. I used it right here. So if we see the word continuously, we need to think this formula, which a lot of times is called PERT. Because it looks like PERT, you just need to remember the RT goes in the exponent. So that means we're using our new formula, PERT. A of T equals P e to the R T. This is continuous. Now, don't let this trip you up. Is this a decimal? Yes. It is still a percentage, though. We need to convert it into a proportion. Boop, boop. 0.045. Always convert. Convert your annual rate into a proportion. Move your decimal. So if we write a model, we're using this one. We've got A of T equals P, which is going to be 2,000. E, do we need to put anything there? No. This is a number. It's approximately 2.718 blah, blah, blah. It's like pi. It just is what it is. R, got 0.045 times T. This is our formula. We can graph this. Desmos knows what that is. 2,000 e to the 0.045 x. It will graph it. So the question is, how much money will Ellie have in her account after 5 years? So that's going to be our t equals 5. So we want to know what is a of 5, our amount after 5 years, 2,000 e to the 0.045 times 5. So let's go in here. And I've already got this, so I'm just going to do times. Need to put it in parentheses because Desmos wants to know that we're still in our exponent, times 5, and we get, Ellie will have $2,504.65. So interest on a credit card is bad. Interest on a bank account is good. It means we get more money. Now, we talked about interest on credit cards can be like 14%, 23%, maybe even 40%. For any of you that have bank accounts, go into your bank account and see how much interest you got. Because I'm going to bet it's probably like a penny or two. Your interest rate on your bank account is typically pretty low. Not anywhere near as high as it is for credit cards. How much of an initial investment would Ellie need to reach $40,000 after 20 years? So now, our initial investment, we're looking for P. So we're going to take that 2,000 out and put a P in, e to the 0.045 t equals a of t. We want to find now what is this value. And so we want to know how much we need to reach 40,000. So that's our amount, right? And so that means that this is going to become 40,000. And it's after 20 years, so that means t is 20. So this is really a of 20 equals p e to the 0.045 times 20. Well, this quantity is just a number, right? So I have p times this. So that means I can solve for p by dividing by e to the 0.045 times 20 on both sides. And we get P is equal to 40,000 divided by E to the 0.045 times 20. And then we can put that into our calculator. We've got 40,000 divided by E, remember our calculator knows what that is, 0.045 times, put it in parentheses so it stays in the exponent, times 20. And so we get that we would need to invest $16,262.7, and then let's talk about this last decimal point. No matter what that number is, I'm gonna round up. If I round down, I won't have enough money to reach my target, so I'm gonna round up. It means that she's gonna be a little bit over 40,000, but we would rather be a little bit over our target than anywhere under our target. So we'll always round that up. All right, so that's how much we would need to invest. All right, so our last one. Jennifer has $2,000 and is looking to invest. She would like to end up with at least $2,500 after 5 years. What rate would Jennifer need if her money is compounded twice a year? So let's go through each part. She has $2,000, so that's gonna be our principal, no matter what. That's all we got. And she wants to invest. She wants to end up with $2,500, so that's our amount after time t. How long? 5 years. So that's t. So this is really a of 5. So our amount is 2,500. Our t is 5 years. And then we want to know what the rate is. So rate, question mark. And so if we put this in our formula, we've got a of t equals p times 1 plus. Then we got to figure out how many times we're compounding per year. And so here we've got twice a year, so that's going to be our n. So we've got r over n to the nt. This is the formula we're going to use. And so let's put our values in. We got 2,500 equals 2,000 times 1 plus our rate, which we don't know, but we want to find, divided by n, which is 2, to the 2 times 5. All right, so we got to solve. So first thing we're going to do to solve is divide by 2,000. And so over here, we're going to end up with 12.5. We're going to end up with 1.25 equals 1 plus r over 2 to the 10th. Now we need to get rid of this exponent. How do we get rid of an exponent? We use a root. So we're going to take the 10th root on either side. In Desmos, you can do this using the functions. If you go to miscellaneous, we're going to click this one that says n root. And then you can put in 10 and then 1.25. And so what you want to do here is not round. So I'm going to leave this like this. Do not round that value. And here we just get 1 plus r over 2. So now what I'm going to do is subtract 1 from both sides. And I get now the 10th root of 1.25 minus 1 equals r over 2. And over here I can just go minus 1. So I'm keeping track of everything I'm doing. Do not round this number. Now I got to get rid of the 2. So I'm going to multiply by 2 on both sides, multiplying everything by 2. And so we're going to put this in parentheses. And we're going to multiply by 2. And so then we get r is equal to 0.04, let's say 5. Okay, and so then we could say we need approximately 4.5%. If we want to make sure that we have at least that, we are going to go ahead and round this up.